双语音标领航，注音阅读启蒙，叶兴阳有声读物。
A History of Science, Volume 2, by Henry Smith Williams, M.D., LL.D., assisted by Edward H. Williams, M.D., in 5 volumes. Volume 2. Contents. Book 2. Chapter 1, Science in the Dark Age. Chapter 2, Medieval Science among the Arabians. Chapter 3, Medieval Science in the West. Chapter 4, The New Cosmology Copernicus to Kepler and Galileo. Chapter 5, Galileo and the New Physics. Chapter 6, Two Pseudosciences Alchemy and Astrology. Chapter 7, From Paracelsus to Harvey. Chapter 8, Medicine in the 16th and 17th centuries. Chapter 9, Philosopher-Scientists and New Institutions of Learning. Chapter 10, The Successors of Galileo in Physical Science. Chapter 11, Newton and the Composition of Light. Chapter 12, Newton and the Law of Gravitation. Chapter 13, Instruments of Precision in the Age of Newton. Chapter 14, Progress in Electricity from Gilbert and von Guericke to Franklin. Chapter 15, Natural History to the Time of Linnaeus. Appendix, A History of Science Book to the Beginnings of Modern Science. The studies of the present book cover the progress of science from the close of the Roman period in the 5th century AD to about the middle of the 18th century. In tracing the course of events through so long a period, a difficulty becomes prominent which everywhere besets the historian in less degree a difficulty due to the conflict between the strictly chronological and the topical method of treatment. We must hold as closely as possible to the actual sequence of events, since, as already pointed out, one discovery leads on to another. But, on the other hand, progressive steps are taken contemporaneously in the various fields of science. And if we were to attempt to introduce these in strict chronological order, we should lose all sense of topical continuity. Our method has been to adopt a compromise, following the course of a single science in each great epoch to a convenient stopping point, and then turning back to bring forward the story of another science. Thus, for example, we tell the story of Copernicus and Galileo, bringing the record of cosmical and mechanical progress down to about the middle of the 17th century, before turning back to take up the physiological progress of the 15th and 16th centuries. Once the latter stream is entered, however, we follow it without interruption to the time of Harvey and his contemporaries in the middle of the 17th century, where we leave it to return to the field of mechanics as exploited by the successors of Galileo, who were also the predecessors and contemporaries of Newton. In general, it will aid the reader to recall that, so far as possible, we hold always to the same sequences of topical treatment of contemporary events. As a rule, we treat first the cosmical, then the physical, then the biological sciences. The same order of treatment will be held to in succeeding volumes. Several of the very greatest of scientific generalizations are developed in the period covered by the present book. For example, the Copernican theory of the solar system, the true doctrine of planetary motions, the laws of motion, the theory of the circulation of the blood, and the Newtonian theory of gravitation. The labors of the investigators of the early decades of the 18th century, terminating with Franklin's discovery of the nature of lightning and with the Linnaean classification of plants and animals, bring us to the close of our second great epoch, or, to put it otherwise, to the threshold of the modern period. Science in the dark age. An obvious distinction between the classical and medieval epochs may be found in the fact that the former produced, whereas the latter failed to produce, a few great thinkers in each generation who were imbued with that skepticism which is the foundation of the investigating spirit, who thought for themselves and supplied more or less rational explanations of observed phenomena. Could we eliminate the work of some score or so of classical observers and thinkers, the classical epoch would seem as much a dark age as does the epoch that succeeded it. But immediately we are met with the question, why do no great original investigators appear during all these later centuries? We have already offered a part explanation in the fact that the borders of civilization, where racial mingling naturally took place, were peopled with semi-barbarians. But we must not forget that in the centers of civilization all along there were many men of powerful intellect. Indeed, it would violate the principle of historical continuity to suppose that there was any sudden change in the level of mentality of the Roman world at the close of the classical period. We must assume, then, that the direction in which the great minds turned was for some reason changed. Newton is said to have alleged that he made his discoveries by intending his mind in a certain direction continuously. It is probable that the same explanation may be given of almost every great scientific discovery. Anaxagoras could not have thought out the theory of the moon's phases. Aristarchus could not have found out the true mechanism of the solar system. Eratosthenes could not have developed his plan for measuring the Earth. Had not each of these investigators intended his mind persistently towards the problems in question. Nor can we doubt that men lived in every generation of the Dark Age who were capable of creative thought in the field of science. Had they chosen similarly to intend their minds in the right direction. The difficulty was that they did not so choose. Their minds had a quite different bent. They were under the spell of different ideals. All their mental efforts were directed into different channels. What these different channels were cannot be in doubt. They were the channels of Oriental ecclesiasticism. One all-significant fact speaks volumes here. It is the fact that, as Professor Robinson points out, from the time of Boethius, died 524 or 525 AD, to that of Dante, 1265 to 1321 AD. There was not a single writer of renown in Western Europe who was not a professional churchman. All the learning of the time, then, centered in the priesthood. We know that the same condition of things pertained in Egypt, when science became static there. But, contrariwise, we have seen that in Greece and early Rome the scientific workers were largely physicians or professional teachers. There was scarcely a professional theologian among them. Similarly, as we shall see in the Arabic world, where alone there was progress in the medieval epoch, the learned men were, for the most part, physicians. Now the meaning of this must be self-evident. The physician naturally intends his mind towards the practicalities. His professional studies tend to make him an investigator of the operations of nature. He is usually a skeptic, with a spontaneous interest in practical science. But the theologian intends his mind away from practicalities and towards mysticism. He is a professional believer in the supernatural. He discounts the value of merely natural phenomena. His whole attitude of mind is unscientific. The fundamental tenets of his faith are based on alleged occurrences which inductive science cannot admit, namely, miracles. And so the minds intended towards the supernatural achieved only the hazy mysticism of medieval thought. Instead of investigating natural laws, they paid heed as, for example, Thomas Aquinas does in his Summa Theologia, to the acts of angels, the speaking of angels, the subordination of angels, the deeds of guardian angels, and the like. They disputed such important questions as, how many angels can stand upon the point of a needle? They argued pro and con as to whether Christ were coeval with God, or whether he had been merely created in the beginning, perhaps ages before the creation of the world. How could it be expected that science should flourish when the greatest minds of the age could concern themselves with problems such as these? Despite our preconceptions or prejudices, there can be but one answer to that question. Oriental superstition cast its blight upon the fair field of science, whatever compensation it may or may not have brought in other fields. But we must be on our guard lest we overestimate or incorrectly estimate this influence. Posterity, in glancing backward, is always prone to stamp any given age of the past with one idea, and to desire to characterize it with a single phrase, whereas in reality all ages are diversified, and any generalization regarding an epoch is sure to do that epoch something less or something more than justice. We may be sure, then, that the ideal of ecclesiasticism is not solely responsible for the scientific stasis of the Dark Age. Indeed, there was another influence of a totally different character that is too patent to be overlooked, the influence, namely, of the economic condition of Western Europe during this period. As I have elsewhere pointed out, Italy, the center of Western civilization, was at this time impoverished, and hence could not provide the monetary stimulus so essential to artistic and scientific no less than to material progress. There were no patrons of science and literature such as the Ptolemies of that elder Alexandrian day. There were no great libraries, no colleges to supply opportunities and afford stimuli to the rising generation. Worst of all, it became increasingly difficult to secure books. This phase of the subject is often overlooked, yet a moment's consideration will show its importance. How should we fare today if no new scientific books were being produced, and if the records of former generations were destroyed? That is what actually happened in Europe during the Middle Ages. At an earlier day, books were made and distributed much more abundantly than is sometimes supposed. Bookmaking had, indeed, been an important profession in Rome, the actual makers of books being slaves who worked under the direction of a publisher. It was through the efforts of these workers that the classical works in Greek and Latin were multiplied and disseminated. Unfortunately, the climate of Europe does not conduce to the indefinite preservation of a book. Hence, very few remnants of classical works have come down to us in the original from a remote period. The rare exceptions are certain papyrus fragments found in Egypt, some of which are Greek manuscripts dating from the 3rd century BC. Even from these sources, the output is meager, and the only other repository of classical books is a single room in the buried city of Herculaneum, which contained several hundred manuscripts, mostly in a charred condition, a considerable number of which, however, have been unrolled and found more or less legible. This library in the buried city was chiefly made up of philosophical works, some of which were quite unknown to the modern world until discovered there. But this find, interesting as it was from an archaeological standpoint, had no very important bearing on our knowledge of the literature of antiquity. Our chief dependence for our knowledge of that literature must still be placed in such copies of books as were made in the successive generations. Comparatively few of the extant manuscripts are older than the 10th century of our era. It requires but a momentary consideration of the conditions under which ancient books were produced to realize how slow and difficult the process was before the invention of printing. The taste of the book-buying public demanded a clearly written text, and in the Middle Ages it became customary to produce a richly ornamented text as well, the script employed being the prototype of the modern printed text. It will be obvious that a scribe could produce but a few pages at best in a day. A large work would therefore require the labor of a scribe for many months, or even for several years. We may assume, then, that it would be a very flourishing publisher who could produce 100 volumes all told per annum, and probably there were not many publishers at any given time, even in the period of Rome's greatest glory, who had anything like this output. As there was a large number of authors in every generation of the classical period, it follows that most of these authors must have been obliged to content themselves with editions numbering very few copies, and it goes without saying that the greater number of books were never reproduced in what might be called a second edition. Even books that retained their popularity for several generations would presently fail to arouse sufficient interest to be copied, and in due course such works would pass out of existence altogether. Doubtless many hundreds of books were thus lost before the close of the classical period, the names of their authors being quite forgotten, or preserved only through a chance reference, and of course the work of elimination went on much more rapidly during the Middle Ages, when the interest in classical literature sank to so low an ebb in the West. Such collections of references and quotations as the Greek anthology and the famous anthologies of Stobaeus and Athanasius and Eusebius give us glimpses of a host of writers. More than 700 are quoted by Stobaeus, a very large proportion of whom are quite unknown except through these brief excerpts from their lost works. Quite naturally, the scientific works suffered at least as largely as any others in an age given over to ecclesiastical dreamings. Yet in some regards there is matter for surprise as to the works preserved. Thus, as we have seen, the very extensive works of Aristotle on natural history, and the equally extensive natural history of Pliny, which were preserved throughout this period, and are still extant, make up relatively bulky volumes. These works seem to have interested the monks of the Middle Ages, while many much more important scientific books were allowed to perish. A considerable bulk of scientific literature was also preserved through the curious channels of Arabic and Armenian translations. Reference has already been made to the Almagest of Ptolemy, which, as we have seen, was translated into Arabic, and which was at a later day brought by the Arabs into Western Europe and, at the instance of Frederick II of Sicily, translated out of their language into medieval Latin. It remains to inquire, however, through what channels the Greek works reached the Arabs themselves. To gain an answer to this question, we must follow the stream of history from its Roman course eastward to the new seat of the Roman Empire in Byzantium. Here civilization centered from about the 5th century AD, and here the European came in contact with the civilization of the Syrians, the Persians, the Armenians, and finally of the Arabs. The Byzantines themselves, unlike the inhabitants of Western Europe, did not ignore the literature of Old Greece. The Greek language became the regular speech of the Byzantine people, and their writers made a strenuous effort to perpetuate the idiom and style of the classical period. Naturally, they also made transcriptions of the classical authors, and thus a great mass of literature was preserved, while the corresponding works were quite forgotten in Western Europe. Meantime, many of these works were translated into Syriac, Armenian, and Persian, and when later on the Byzantine civilization degenerated, many works that were no longer to be had in the Greek originals continued to be widely circulated in Syriac, Persian, Armenian, and, ultimately, in Arabic translations. When the Arabs started out in their conquests, which carried them through Egypt and along the southern coast of the Mediterranean, until they finally invaded Europe from the west by way of Gibraltar, they carried with them their translations of many a Greek classical author, who was introduced anew to the Western world through this strange channel. We are told, for example, that Averroes, the famous commentator of Aristotle, who lived in Spain in the 12th century, did not know a word of Greek and was obliged to gain his knowledge of the master through a Syriac translation, or, as others alleged, denying that he knew even Syriac, through an Arabic version translated from the Syriac. We know, too, that the famous chronology of Eusebius was preserved through an Armenian translation, and reference has more than once been made to the Arabic translation of Ptolemy's great work, to which we still apply its Arabic title of Almagest. The familiar story that when the Arabs invaded Egypt they burned the Alexandrian library is now regarded as an invention of later times. It seems much more probable that the library had been largely scattered before the coming of the Muslims. Indeed, it has even been suggested that the Christians of an earlier day removed the records of pagan thought. Be that as it may, the famous Alexandrian library had disappeared long before the revival of interest in classical learning. Meanwhile, as we have said, the Arabs, far from destroying the Western literature, were its chief preservers. Partly at least because of their regard for the records of the creative work of earlier generations of alien peoples, the Arabs were enabled to outstrip their contemporaries. For it cannot be in doubt that, during that long stretch of time, when the Western world was ignoring science altogether, or at most contenting itself with the casual reading of Aristotle and Pliny, the Arabs had the unique distinction of attempting original investigations in science. To them were due all important progressive steps which were made in any scientific field whatever for about 1,000 years after the time of Ptolemy and Galen. The progress made even by the Arabs during this long period seems meager enough, yet it has some significant features. These will now demand our attention. 2. Medieval science among the Arabians. The successors of Muhammad showed themselves curiously receptive of the ideas of the Western people whom they conquered. They came in contact with the Greeks in Western Asia and in Egypt, and, as has been said, became their virtual successors in carrying forward the torch of learning. It must not be inferred, however, that the Arabian scholars, as a class, were comparable to their predecessors in creative genius. On the contrary, they retained much of the conservative Oriental spirit. They were under the spell of tradition, and, in the main, what they accepted from the Greeks they regarded as almost final in its teaching. There were, however, a few notable exceptions among their men of science, and to these must be ascribed several discoveries of some importance. The chief subjects that excited the interest and exercised the ingenuity of the Arabian scholars were astronomy, mathematics, and medicine. The practical phases of all these subjects were given particular attention. Thus it is well known that our so-called Arabian numerals date from this period. The revolutionary effect of these characters, as applied to practical mathematics, can hardly be overestimated, but it is generally considered, and in fact was admitted by the Arabs themselves, that these numerals were really borrowed from the Hindus, with whom the Arabs came in contact on the East. Certain of the Hindu alphabets, notably that of the Badics of Sumatra, give us clues to the originals of the numerals. It does not seem certain, however, that the Hindus employed these characters according to the decimal system, which is the prime element of their importance. Knowledge is not forthcoming as to just when or by whom such application was made. If this was an Arabic innovation, it was perhaps the most important one with which that nation is to be credited. Another mathematical improvement was the introduction into trigonometry of the sign the half-chord of the double arc instead of the chord of the arc itself, which the Greek astronomers had employed. This improvement was due to the famous Albatenius, whose work in other fields we shall examine in a moment. Another evidence of practicality was shown in the Arabian method of attempting to advance upon Eratosthenes' measurement of the Earth. Instead of trusting to the measurement of angles, the Arabs decided to measure directly a degree of the Earth's surface, or rather 2 degrees. Selecting a level plain in Mesopotamia for the experiment, one party of the surveyors progressed northward, another party southward, from a given point to the distance of 1 degree of arc, as determined by astronomical observations. The result found was 56 miles for the northern degree, and 56 2/3 miles for the southern. Unfortunately, we do not know the precise length of the mile in question, and therefore cannot be assured as to the accuracy of the measurement. It is interesting to note, however, that the 2 degrees were found of unequal lengths, suggesting that the Earth is not a perfect sphere, a suggestion the validity of which was not to be put to the test of conclusive measurements until about the close of the 18th century. The Arab measurement was made in the time of Caliph Abdullah al-Mamun, the son of the famous Harun al-Rashid. Both father and son were famous for their interest in science. Harun al-Rashid was, it will be recalled, the friend of Charlemagne. It is said that he sent that ruler, as a token of friendship, a marvelous clock which let fall a metal ball to mark the hours. This mechanism, which is alleged to have excited great wonder in the West, furnishes yet another instance of Arabian practicality. Perhaps the greatest of the Arabian astronomers was Muhammad ben Jabir al-Batenius, or al-Batani, who was born at Baitan, in Mesopotamia, about the year 850 AD, and died in 929. Albatenius was a student of the Ptolemaic astronomy, but he was also a practical observer. He made the important discovery of the motion of the solar apogee. That is to say, he found that the position of the sun among the stars, at the time of its greatest distance from the Earth, was not what it had been in the time of Ptolemy. The Greek astronomer placed the sun in longitude 65 degrees, but Albatenius found it in longitude 82 degrees, a distance too great to be accounted for by inaccuracy of measurement. The modern inference from this observation is that the solar system is moving through space. But of course this inference could not well be drawn while the Earth was regarded as the fixed center of the universe. In the 11th century, another Arabian discoverer, Arzakel, observing the sun to be less advanced than Albatenius had found it, inferred incorrectly that the sun had receded in the meantime. The modern explanation of this observation is that the measurement of Albatenius was somewhat in error, since we know that the sun's motion is steadily progressive. Arzakel, however, accepting the measurement of his predecessor, drew the false inference of an oscillatory motion of the stars. The idea of the motion of the solar system not being permissible, this assumed phenomenon, which really has no existence in point of fact, was named the trepidation of the fixed stars, and was for centuries accepted as an actual phenomenon. Arzakel explained this supposed phenomenon by assuming that the equinoctial points, or the points of intersection of the equator and the ecliptic, revolve in circles of 8 degrees radius. The first points of Aries and Libra were supposed to describe the circumference of these circles in about 800 years. All of which illustrates how a difficult and false explanation may take the place of a simple and correct one. The observations of later generations have shown conclusively that the sun's shift of position is regularly progressive, hence that there is no trepidation of the stars and no revolution of the equinoctial points. If the Arabs were wrong as regards this supposed motion of the fixed stars, they made at least one correct observation as to the inequality of motion of the moon. 2 inequalities of the motion of this body were already known. A third, called the moon's variation, was discovered by an Arabian astronomer who lived at Cairo and observed at Baghdad in 975, and who bore the formidable name of Muhammad Abul Wifal Bozjani. The inequality of motion in question, in virtue of which the moon moves quickest when she is at new or full, and slowest at the first and third quarter, was rediscovered by Tycho Brahe 6 centuries later, a fact which in itself evidences the neglect of the Arabian astronomer's discovery by his immediate successors. In the 9th and 10th centuries, the Arabian city of Córdoba, in Spain, was another important center of scientific influence. There was a library of several 100,000 volumes here, and a college where mathematics and astronomy were taught. Granada, Toledo, and Salamanca were also important centers, to which students flocked from Western Europe. It was the proximity of these Arabian centers that stimulated the scientific interests of Alfonso X of Castile, at whose instance the celebrated Alphonsine tables were constructed. A familiar story records that Alfonso, pondering the complications of the Ptolemaic cycles and epicycles, was led to remark that, had he been consulted at the time of creation, he could have suggested a much better and simpler plan for the universe. Some centuries were to elapse before Copernicus was to show that it was not the plan of the universe, but man's interpretation of it, that was at fault. Another royal personage who came under Arabian influence was Frederick II, of Sicily, the wonder of the world, as he was called by his contemporaries. The Almagest of Ptolemy was translated into Latin at his instance, being introduced to the Western world through this curious channel. At this time it became quite usual for the Italian and Spanish scholars to understand Arabic, although they were totally ignorant of Greek. In the field of physical science, one of the most important of the Arabian scientists was Alhazen. His work, published about the year 1100 AD, had great celebrity throughout the medieval period. The original investigations of Alhazen had to do largely with optics. He made particular studies of the eye itself, and the names given by him to various parts of the eye, as the vitreous humor, the cornea, and the retina, are still retained by anatomists. It is known that Ptolemy had studied the refraction of light, and that he, in common with his immediate predecessors, was aware that atmospheric refraction affects the apparent position of stars near the horizon. Alhazen carried forward these studies, and was led through them to make the first recorded scientific estimate of the phenomena of twilight and of the height of the atmosphere. The persistence of a glow in the atmosphere after the sun has disappeared beneath the horizon is so familiar a phenomenon that the ancient philosophers seem not to have thought of it as requiring an explanation. Yet a moment's consideration makes it clear that, if light travels in straight lines and the rays of the sun were in no wise deflected, the complete darkness of night should instantly succeed to day when the sun passes below the horizon.